Hello everyone. Today we're going to take a look at graphing tangent graphs. So to start off, let's just take a look at the table of values here. Um, so tan is a little different than sine and cosine, and we're going to see why here in a bit. Just a few things. So tan, um, yeah, I mean it's going to stand out right away. Sine and cosine share a couple of characteristics, right? They have that sinusoidal axis, which is the middle part of that graph. They repeat right every 360 degrees. They repeat, so they never go above one. They never go below -1. And that all makes sense because if you think about like what sine is and what cosine is, right? Sine is the ratio of the opposite to the hypotenuse, and cosine is also a ratio, but it's to the adjacent to the hypotenuse. And just under the definition of a triangle, the opposite and the adjacent can never be larger than the hypotenuse. So it makes sense that that ratio is never going to be larger than 1. But with tangent, it's a little different. So with tangent, we don't have a sinusoidal axis anymore because there is still a repetition going on, but the pattern is a little different. It's not that wave pattern. It looks a little different, and we're going to see what it looks like here in a second. And also, the values are not limited to numbers between 1 and -1 because, again, by definition, tangent is the ratio of the opposite over the adjacent. And there is no characteristic within a triangle that says that the opposite has to be larger than or the opposite has to be smaller than the adjacent. Either can be larger or smaller. So with that in mind, that ratio could be any value. So a couple of things here. We look at a table of values that is tan. So if theta was -pi/2, what ends up happening is when we take the tan of -pi/2, and if you try that in your calculator, what you're going to get is you're going to get a math error. You're going to get an answer that is undefined. And the reason that is because if we looked at our unit circle for a second, right? -pi/2 and +pi/2. So pi/2 is here, and -pi/2 is down at the bottom. And the thing is, when you look at this point here is 0, 1, and this is 0, -1, right? And we think about what tan is. Tan theta is y over x. So the issue here is that x for these 2 points is 0, and what happens when we divide by 0 is we get something that is undefined. So what that's going to look like in terms of the graph of this thing is we are going to have what's called asymptotes. So these dotted red lines here are called asymptotes. We have one here at -pi/2 and another one here at +pi/2, and then um, 0 is 0. Right, and that, again, that makes sense because if you take a look at the point over here, 0, this is 1 comma 0. So 0 divided by 1 is still 0. So what an asymptote is, and you may not have seen an asymptote before, maybe you have, but you might not have. What an asymptote is graphs will approach a point but never actually hit it. And we've talked about this when we talked about series, right? We talked about a series can converge on a point. And again, what that means is that it'll get closer and closer and closer, but it won't necessarily hit that point. We probably would have seen asymptotes last year when we talk about log graphs and exponential graphs and things like that. So this is a vertical asymptote here at -2, and what happens is my graph gets closer and closer and closer and closer, but it never hits -2. And same thing here at +pi/2, it gets closer and closer and closer and closer, but never hits it. So with that in mind, if we take a look at things like our domain and our range, well, our domain for this graph is that it can never equal an asymptote, right? X cannot be one of our asymptotes. And the way that we find that is we say, okay, well, here's an asymptote at -pi/2, and here's another asymptote at pi/2, which is pi units away, and there's going to be another asymptote pi units away, another asymptote pi units away. So we're going to say that it can't be pi/2 plus n times pi, where n could be any integer. Now, this graph also does not have maximums and minimums, right? So again, so here are some of these differences, right? For sine and cosine, the domain was XER, right? X and ohms are the real numbers because we can throw any value in for X and we're going to get an answer. The range for a sine and a cosine graph was it had to lie in between my highest and my lowest points, and it can't go above or below those. For the tangent graph, there are no maximum or minimum points. If we take a look at the graph here, what we see is that it keeps going up forever and ever and ever, and it keeps going down forever and ever and ever. There is no maximum or minimum value. So what that means is the range now is YER. The period for a tangent graph is pi. So again, here's another difference. For sine and cosine, the period was 2 pi. And that makes sense because it would do one full revolution and we get back to our terminal arm and then we'd have that exact same value. So that's why it'd be 2 pi. For tangent, it's a little different. Yeah, it's going to repeat every 2 pi, but there is a sooner point in time in which it repeats. And when that is if we think about our cast rule for a second, right? CAST, right? Whatever positive tangent, we'll start with positive. If we have a positive tangent, that positive tangent is going to be up here in my first quadrant at some reference angle, right? But it's also going to be down here at the same reference angle. So what that means is that this line, this tangent value, is going to repeat, or it's going to hit another one exactly pi units or 180 units, depending on if we're talking about degrees or radians, right? It's going to hit the other value half a rotation away. So what that means is that our pattern is going to repeat every half rotation. And our asymptotes are just our domain, right? It's the same value. So it's pi over 2 plus pi n. Our x-intercepts, on the other hand, a little different, but it's going to be 0, right? It's going to be this 0 down here where we have an x-intercept, and it's going to happen again every pi units because that's our period. So there's going to be 1 here, there's going to be 1 over here at 6 pi over 6, which is pi, there's going to be 1 down here at negative pi, and so on and so on and so on. So how do we graph these things? Well, we're going to graph these things the same way that we graph sine and cosine. We're going to look at the transformations. So transformations on tangent graphs work the same as they do for sine and cosine. So let's stop and just take a look at how we can find some key pieces of information first, and then we'll take a look at how we can actually graph these things. So to find the domain, range, period, and vertical asymptotes, we're going to do the following things. We have formulas, right? We have formulas that can allow us or help us to find these. So for example, the domain is going to be x is not allowed to be 90 degrees or pi over 2 divided by b plus 180 divided by b, or over here plus pi divided by b, and then there's also this h value. And this kind of makes sense because if we think about this for a second, if we go back to what our graph looked like, right, or what our domain looked like for the basic tan function, what's happening is we're going to have a asymptote that is at pi over 2, and then it's going to add pi each time. And what happens is that this central point here doesn't get affected by A or B. It doesn't move based on A or B. So what's going to happen is my asymptotes, depending on my B value, are going to expand or shrink in relation to this point 0, 0. So what that means is that it's pi over 2 units to the right of 0 and pi over 2 units to the left of 0. But if it's shrinking by some b value, that distance is going to go down by, again, that b value. So if b was 2, for example, instead of being pi over 2 and pi over 2, it's going to shrink by half, and it's going to be pi over 4 and pi over 4. Then what happens is we have a horizontal translation that will take this entire graph and shift it left or right. So that's why with this h value, we're going to add that on, right? We're going to add on h or add on h, depending on radians or degrees, right? And then that's going to be where our graph happens. Then we know that because tangents, or because any of these trig functions repeat the pattern every time we go through a full period, right, we're going to find that period the same way we would for sine and cosine. We're going to take the period of the original function and divide it by b. So with a tangent graph, the original period is pi, or 180. So we're going to take that value and divide it by b, and that's going to tell us where our domains are. Now, it's a pretty big formula. It's a complex formula, and it's not one that I would necessarily want anybody to memorize. I think you're better off knowing what this formula does. So what this formula does is it takes your first asymptote, right? So this whole bit of it right here, that's my first asymptote, right? So if you can find some easier way of finding your first asymptote without actually having to um, plug a formula or figure it out kind of using patterns, then what it does is it adds the period. Right, and that makes sense because that's when my pattern resets, right? So one period away, we'll have another asymptote, and then one period away, we'll have another asymptote, and so on and so on and so on. The range, simply stated, is y is an element of the real numbers. Okay. Another kind of way of thinking about this is if you know where your asymptotes are, then we know what y can't be, right? So if I know where my first asymptote is, and I know that I'm adding a period each time, right? Y can't, or x, sorry, can't be those values. My range, YER. Simple, done, next question, right? And that makes sense, again, because it's a ratio, right? When we're talking about ratio of the opposite to the adjacent, there's no rule that's saying one has to be bigger than the other, so they could be any ratio, so we got to consider that, okay? The period is going to be 180 over b or pi over b, depending on if we're talking about degrees or radians. And again, we talked about why it's 180 and pi this time instead of the 2 pi or 360 like sine and cosine. And again, we already talked about our asymptotes. The asymptote here is going to be exactly the same thing as the domain, except it's going to be x equals instead of x can't equal. All right, so let's take a look at how we actually graph one of these things. So let's start off with this one right here. Y is equal to 3 theta plus 1. So the first thing that we're going to want to do when we're trying to graph these things is pick out your key points, right? A, B, H, and K, and then decide what do those mean to my graph, right? So the A value here is 1, right? It's the number that's in front of my tan, so 1, right? The B value is 3, right? My H, there is no H written there, so it's going to be 0, and my K is 1, right? And then what did those mean? Well, an A value of 1 means I have a vertical stretch of 1, so it's not going to change. A B value of 3 means that there's a horizontal stretch of 3, or in other words, it's going to shrink it by a factor of 3. An H value of 0 means my graph does not shift left or right, and a K value of 1 means it's going to shift up 1 unit. Okay, so then it's a matter of finding out some key information. So again, easiest one to find here, the range, y is an element of the real numbers. Okay, our period we find by saying, well, the original period divided by 3. So now my new period is going to be pi over 3. Okay, and then what we can do is we can take these values and plug it into my formula to figure out where my asymptotes are going to be. So if we're talking about either degrees or radians, right? With this question, it's not really stating one or the other, but I've decided to use radians, so we're going to use radians. So again, we have a formula that we can use. So in this case, B was 3, right? And H is 0, and B is 3. So what I can do is I can plug those numbers in, and I'm going to pi over 6 plus 0, which is pi over 6, plus pi over 3n. Right? And then, or 2 pi over 6n, right, if we talk about finding common denominators. So what that means is now I can go back to my graph and say, okay, I'm going to have my first asymptote at pi over 6, and then I'm going to have an asymptote every pi over 3 units later. So if we take our line tool here, okay, so we have our first asymptote here at pi over 6. And then we have another asymptote, pi over 3 units later, so or 2 pi over 6. So pi over 6, 2 pi over 6, 3 pi over 6, right? 2 pi over 6 units later, so to go from pi over 6 to pi over 3 is 1 pi over 6, and then pi over 2 is 2 pi over 6. So there's another asymptote right here. So what that means is and then if I go the other direction, same thing, right? So we have another asymptote right here at negative pi over 6, and then another asymptote over here at negative pi over 2, and so on and so on and so on, right? It goes on because the period of the pattern is going to continue. So now what we can do is there's two strategies, just like with sine and cosine. And I'm going to show you the table, just like we did before. And then I'm going to talk about how I would do a question like this with using these patterns, okay? So with the table, here is our original column where negative pi over 2 is undefined, negative pi over 4 is equal to negative 1, 0, 0, pi over 4, 1, and then pi over 2 undefined. So what we're going to do is same thing as before. We're going to take the x values and divide them by b and add h. So negative pi over 2, right? Negative pi over 2 divided by 3 is negative pi over 6, and then plus 0 is negative pi over 6. Okay, negative pi over 4 divided by 3, and then plus 0 is negative pi over 12. And then 0 divided by 3 plus 0 is 0. Positive pi over 4 becomes positive pi over 12, and positive pi over 2 becomes positive pi over 6. Do the same thing with the y values. We're going to multiply by a and add k. Well, a here was 1, and k is 1 as well. So undefined, what ends up happening is when something is undefined, it's going to remain undefined, right? So this is just undefined. Okay, so negative 1. So negative 1 times 1 is negative 1, and then negative 1 plus 1 is 0. And then 0 times 1 is 0. 0 plus 1 is 1. And then 1 times 1 is 1, and 1 plus 1 is 2. And then we're back to being undefined. So then what we can do now is we can go back to our plot, or back to our graph, and plot these points. So negative 12, 0. So negative 12 is in between here. So it'd be negative 12, 0 would be right here. 0, 1 is there. And then positive pi over 12, 2. Positive pi over 12, 2. So what this is going to do is the graph is going to attach these points, and it's going to get closer and closer and closer and closer to my asymptote, but never quite touch it. And then we're going to go off the same thing in the positive direction, so we're going to get closer and closer and closer and closer to my asymptote, but never quite touch it. But then what's going to happen is this pattern will repeat. So if I take this and I grab this graph and I move it, goes there, goes there, right? Does the same thing here, does the same thing here, and it goes on like that forever and ever and ever. Okay? So there's a couple of things I'd like to point out before we check out the next question. And they are, notice my middle point here, this one that's right in the middle. Originally that point was 0, 0, and now the coordinates of this point are 0, 1. Okay? And the reason I wanted to point this out is that these two numerical values here are going to match h and k, right? So because my original point was 0, 0 for this graph, right, for a tangent graph, it's normally at 0, 0. When you multiply 0 by b, you get 0. When you multiply 0 by a, you get 0. So the only thing that's going to change these values are h and k. So for any tangent graph, the middle is always going to be at h comma k, right? And then what's going to end up happening is the vertical stretch for this graph is going to tell us how much it gets stretched vertically. I guess that makes sense. But what that means is that this distance from my 0, 0 to my next point over is going to be equal to my a value. Just like with my sine and cosine graphs, the distance from my sinusoidal axis to my my crest and my troughs were the a value, right? The same thing happens here. Now, be aware that with a tan graph, it's not amplitude. Amplitude applies specifically to waves. So with a tan graph, we're going to talk about vertical stretch as opposed to amplitude. But the vertical stretch here is going to be equal to, my a value is going to be the distance from my middle to this point here, right? Where normally this distance was supposed to be 1 unit, right? This distance was 1 unit. So from my pi over 4 up here to 1, right? Normally it was 1 unit, so what's going to happen is when I stretch that graph, it's going to stretch it by a factor of a, so 1 times a, right? That distance is going to be a units. And the same thing in the negative direction, right? Down here at -1, that distance is going to be a units. So the nice thing about that is once you start figuring out what a, b, h, and k are going to do to your graph, you can start graphing this without making a table. Okay, so let's try another one. So again, what I'd like to do is find my a value. So a is 2. Sorry, a is not 2. A is 1. B is 2. H is pi over 3, and it's positive, right? And then k is 2. So then what does that do? Well, an a value of 1 means that my vertical stretch is 1. A b value 2 means my horizontal stretch is going to be half, or 1 over 2. Right? My h value being pi over 3 means that I have a horizontal translation of pi over 3 units to the right. And my vertical translation being 2 means that I have a vertical translation of 2 units up. So again, when it comes time to graph these things, yeah, you can make a table of values and use the values that I provided in the previous slide, right? Use this as my original, and then just do your B and H calculations like you would for any graph. Really, it doesn't have to be tangent. But what I like to do when I'm doing these questions is I like to save myself a little bit of time by recognizing what's going to happen. So what I mean by that is, again, we said that the middle point is going to be h comma k. So right away, what I know is that my pi over 12, 2 pi over 12, 3 pi over 12, 4 pi over 12 is pi over 3 is the x value of my middle, and 2 is the y value of my middle, right? So my h comma k. So this point here is h comma k. And what I also know is that my period for this graph is pi over b. So in this case, it's going to be pi over 2, right? So to go from asymptote to asymptote is pi over 2 units, which means that if I know where the middle is, I can go pi over 4 units to either side in order to get my 2 asymptotes. And why pi over 4? Because it's half the distance, right? So if the distance from asymptote to asymptote is pi over 2, then the distance from one asymptote to the middle will be half of that, so pi over 4. And then from the middle to the next asymptote, the other half, so another pi over 4. So if we're talking about units of pi over 12 here, that means we're going back 1, 2, 3 pi over 12, and that's where I'm going to find my first asymptote here at pi over 12. And then same thing the other direction, so 1, 2, 3 pi over 12 at 7 pi over 12. Right? And then what you'll notice is that the distance from pi over 12 to 7 pi over 12 is 6 pi over 12, and 6 pi over 12 is my period, right? That's pi over 2. Then what I like to do is look at, okay, well, I know that the distance from the middle to an asymptote is pi over 4. So again, halfway between those two distances is where I'm going to find this next value that I'm looking for, my a, what my a is going to do to it, right? So here, when we looked at the original graph, when we go from negative pi over 2 to pi over 2, that's my period, right? Negative pi over 2 to the middle, that's half my period. Well, from the middle to these points in between is a quarter of my period, right? So to go from here to here is, sorry, and to go from negative pi over 2 to the positive pi over 2, right? That's one full period, right? To go from negative pi over 2 to 0, that was half a period, right? But then to go from 0 to this point here, that's a quarter of the period. So what I can do is if I take my period and I divide it by 4, I get pi over 8, right? So what's going to happen is right in between these 2 points right here, I'm going to have my kind of high point for the graph, and my low point for the graph is going to be on the other side, right? So again, what I'm going to do is if my a value is 1, the height difference between this high point and my middle is 1 unit. So if my middle is here at 2, then my high point is up here at 3. And again, right in between my middle and my asymptote is here, right? So if I have a value of 1, then my low point is going to be down here at -1. So now if I attach these points and trace along to my asymptote, I get a graph that looks something like this. Right? Not to say that, again, you can use the table, right? What we could do is we could take that table of values, the negative pi over 2, undefined, negative pi over 4, undefined, 0, sorry, not undefined, negative pi over 4, -1, 0, 0, pi over 4, +1, and pi over 2, undefined, and then apply my values, right? So my b and my h values. So if we take the negative pi over 2, so it's x over b plus h, right? So if I take my negative pi over 2 and I divide it by 3, I get negative pi over 6 and then plus h, and I'll keep getting those values, right? And I can fill in my table and then plot those points this way. But again, what I like to do is I like to take the pattern and help me simplify my work. Okay. Um, so let's do one more. Let's take a look at one more question, and maybe at this point try to pause the video and try it yourself. And then once you're ready, start the video back up and follow along. So let's do it here. So A is 1, B is 3, H is positive 30, and K is 1. So that means I'll have a vertical stretch of 1, a horizontal stretch of 1/3, a horizontal translation of 30 units to the right, and a vertical translation of, 1 unit up. So again, what I'm going to do is I'm going to find my middle by saying h comma k. So there's my middle. Okay. My period is, and this time we're talking about degrees, right? So it's going to be 180 divided by b, or 180 divided by 3, which is 60 degrees. So to go from asymptote to asymptote is 60. So to go from asymptote to middle is going to be 30 degrees. So 30 plus 30, I have an asymptote here at positive 60, and 30 minus 30, I have an asymptote here at 0. Then, to find my high and low points, again, my high point is going to be 1 above the middle, and my low point is going to be 1 below the middle, and the x value of those are in between my middle and my asymptote. So if it takes 30 degrees to get from my middle to my asymptote, my in between that is going to be 15 degrees more, or in other words, here at 45. So at 45, comma 1, I've got my high point. My graph does this, and then 15 degrees the other direction, so 30 minus 15 is 15, right? And 15, and then 1 minus 1 is 0, so I have this point here, and if I attach them, I get my graph. Okay, so again, for each of these, so I suppose we should probably be talking about domain range. So if I take a look at my domain here, right? What can't x be? And I find it's easier to do domain and range once you have it graphed. So what can't my domain or what can't my x values be? They can't be the asymptote. So what I'm going to do is I'm going to find my first asymptote. So I have an asymptote here at 0, right? So x can't be 0. And then I have an asymptote every 60 units later, or every pi or period later. So plus 60n, where n is an element of the integers. And then range for tan graphs are y is an element of the real numbers. Okay, so hopefully that was clear. And again, I'm not saying use one strategy or another, right? If you're really comfortable using these tables, and again, we use the table exactly the same way we use the table for sine and cosine, right? We take the x value divided by b plus h, take the y value multiplied by a plus k, right? Exactly the same. So I would suggest using those if you're comfortable with those. But if you're starting to get, okay, here, there's a pattern here, right? Like when I go halfway, it does this, or when I go a quarter of the way, it does this. So if you're getting comfortable and you want to try that, I would suggest that because it saves us a lot of time. And when it comes time to go backwards, which we're going to look at in the next video, it's going to make our lives a lot easier being able to recognize the asymptote just from my graph without having to try to do any kind of calculations. All right, so you guys have a great day, and I will see you in the next video.